All right, so it should be recording now, I think. Okay. All right. So, like I said, just two topics that I want to talk about today. The first one is unit vectors, and the second one is dot products. Unit vectors are just another way of representing vector notation. We talked about components. Now we're going to talk about unit vector. And the premise behind it is we've got two unit vectors. We'll call one of them I, and we'll call the other one J. And they look like this. So if I have my Cartesian grid, I is a unit long. So it's 1 unit long, whatever we're measuring in, and it's in the positive x direction. So this would be 1 unit long in the positive x direction, and so this would be our unit vector I. Then J is 1 unit long, but in the y direction, or vertical. That doesn't quite look the same, but it's supposed to be the same. So 1. So this is the unit vector J. We can represent vectors using multiples of I and J. So for instance, if I have, so any vector can be written with these unit vectors I and J, like this. So if I had the vector V and its components were just two numbers, say V1 and V2. So for example, I could have that vector V is equal to 3, 5. What that tells me to do is go to the right 3 and up 5. So this is kind of what we were talking about before. Vector V can also be represented as a linear combination of multiples of I and J. So we could represent this as V1 times the vector I plus V2 times the vector J. And so our example over here would look something like 3I vector, so 3 times the I vector plus 5 times the J vector. Remember, J is vertical and I is horizontal, is another way to represent these two. So these are identical, just different ways to represent those two. So if we had two vectors, so say we had vector V was equal to the components 2, 3. So this tells you to go to the right 2 and up 3. U is -3, say 8. So to make vector U, you would go to the left 3, and then you would go up 8. We can represent these as, in this case, this would be 2I plus 3J. And notice I'm trying to make those vectors bold. And this one would be, U would be -3I plus 8 times the unit vector J. Now, if we needed to do some of those operations, so yesterday we talked about some operations. What is 2U, say, minus 3V? Well, that would be equal to 2 times the vector U, and the vector U is -3I plus 8J, and then plus a -3 times the vector V, which is 2I plus 3J. And so you kind of would distribute and then combine like terms. It kind of is like the I and the J are just two variables. So this would be -3, -6I plus 16J. Let me fix that. So -6I plus 16J minus 6I minus 9j. So I got minus 6i and minus 6i, that gives me minus 12i, and then plus 16j minus 9j, and that would be plus 7j. So that's one way we could represent the resulting vector, or we could put it in component form, which would be minus 12 and 7. All right, so really, I just kind of wanted to show you that. That's another way. Hang on, I'm messing around with this. Sorry. That's another way to represent vectors as a linear combination of this vector, unit vector j, and unit vector I. So it makes it, you'll see in some applications you'll want it in unit vector form. In other applications you'll want it in component form like this, but they can be used interchangeably. They're one and the same. All right, so now what we're going to talk about, the last part of our vector lesson, is something called dot products. So dot products of two vectors, or not necessarily of two, but just of vectors. You can definitely have dot product of three vectors. So it looks like this. Remember, we can represent our vectors with bold lowercase letters u and v here. A dot product, you simply just put the dot. That's exactly what it is, but it's not exactly multiplication. When you take one vector and do a dot product with another vector, what you end up with is not another vector, you end up with a number, not another vector. So remember, when we added vectors, we ended up with a whole nother vector. So we took vector u plus vector v. When we added them together, we got a whole nother vector. When we do a dot product, we get one simple number, just one number. And what that number is equal to, so if u is represented by the components u1, comma u2, and v is represented by v1, comma v2, right? So that's the component form of these two vectors. Then the dot product u dot v is equal to u1 times v1 plus u2 times v2. And so you can see, if I did all of that, I took the product of these two numbers and added it to the product of these two numbers, I would get a number, not another vector. So for example, if I had u was the vector -1, 3, v was the vector 2, -4, and we'll even do another one, w is the vector 1, comma -2. So those are three vectors. Let's find some products, or sorry, some dot products here. So find, first of all, u dot v. And so following this method up here, you take the first two components of one vector, multiply them together, and then you take the second two components of the vectors, both the vectors, multiply them together, and then you add those products. So in this case, we would have -1 times 2 plus 3 times -4, and we would get -14. So I took two vectors, did the dot product, and I ended up with just one number. What happens if I did u dot v, but then that is times w? This is not a dot in here. The only dot is right here. So what's going to end up right here is a number. We actually already figured that out. And then we're going to take that number and multiply by w. We're going to do a scalar multiplication of vector w. I'm not going to worry about parentheses. So -14 times w. And so that would just be -14 times the components 1, -2. And so this would be the components -14, 28. Oops, that needs to be a square bracket. I know what I'm thinking. There we go. All right, what if I said, let's take So notice this ends up being a number, and then I'm multiplying a vector by a number. That gives me a vector. So dot product of two vectors gives me a number. If I take a number times a vector, that gives me a vector. If I take u times 2v, this I would expect to be a number because I'm taking the dot product of two vectors. Yes, one of these vectors is being multiplied by 2, but it's still going to give me a dot product of two vectors, which will give me a number. So this would be -1, 3 for u, and then dot product with twice v. Well, v is 2 and -4, so I've got to multiply each of those by 2. So that would be v4, v4 -8. So this right here is 2v. Now I can find what the dot product is here. So this multiplying these two, or not multiplying, sorry, dot product of these two is going to give me a number. -4 plus -24 gives me -28. All right, so that's the same, and you can also represent this same thing. You can pull this 2 out front and just have this as the dot product of u and v times 2. It would equal the same thing. You'd end up with the same thing. We already know that u dot v is -14. If I multiply that by 2, I get -28. All right, so why are dot products important? Dot products are important because now we can find the angle between two vectors. And that formula looks like this. So cosine of theta, and theta is the angle between two vectors, is equal to the dot product of the vectors divided by the magnitude of each of those vectors multiplied. I'm going to get rid of that dot in here. It's not a dot. I don't want you to think this is another dot product. It's just the magnitude of u times the magnitude of v. So that angle right there, when you solve this, you're going to have to use inverse here because you're going to get a value here, and then you're going to do inverse trig to find out what the actual angle is between the two. So let's do one example, and then we'll talk about what those values mean. So if we were asked to find the angle between u and v, and u is the vector 4, 3, and v is the vector 3, 5. So we need to first find the dot product of these two vectors. We need to find the magnitude of those two vectors. So let's go ahead and find those parts. So u dot v is going to be equal to, you multiply the first two and you get 12, plus you multiply the last two and you get 15. So that's going to be 27. So the numerator is 27. The magnitude of u, remember, is just the square root of this component squared plus this component squared. So that's going to be the square root of 25, which is 5. And the magnitude of v is going to be this, the square root of this component squared plus 5 squared. And that's the square root of 34, which can't be simplified. So those are our parts to put back into this big kind of formula right here. It's big ratio formula. So we can say that the cosine of theta is 27 over 5 times the square root of 34. So the dot product is 27. The two magnitudes multiplied together, it looks like that. Now this part, we have to use inverse trig. So we have to go to our calculator and use cosine inverse, right? So if the cosine of theta is equal to that, then the cosine inverse, or the inverse cosine of that value, is equal to theta. And so you can put that all in your calculator. I did it here earlier. You can see there's 27. So cosine inverse of 27 over 5 times 30 square root of 34 gives me 22.2 degrees. So theta is 22.2 degrees. So if we took these two vectors and we put their tips to each other, the angle between them would be 22.2 degrees. So let's look at these vectors. U is going, starts somewhere, and it goes over 4 and up 3. So, you know, it would look like this way would be 4, and then we would go up 3. So maybe this would be what U looks like. Then V goes over 3, but up 5. So it doesn't go quite as far to the right, but it goes up 2 more. So maybe, let me draw it in a different color. V maybe looks like this. It goes over 3 and up 5. So here's 5, here's 3, here's 4, here's 3. Probably would have been better if I put U bar there, so it looks so not so messed up inside here, right? So those are my two vectors. This is the vector U. I go over 3, over 4, and up 3. This is the vector V. I go over 3 and up 5. The angle theta is this angle right here. Ooh, my pen just got messed up. Hopefully you can see that. There we go. That angle between those two vectors is what we just solved for right here using that formula. And there's a lot of civil engineering and those kinds of problems that need to know the angle between those two vectors. So one last thing I want to talk about is obviously this would be an acute angle. If theta ended up being 180 degrees, then you would have angles, or your vectors would look like this. You'd have one vector going this way, and then 180 degrees would be the other vector would go this way. So that's a possibility. Let me see, I'm just going to kind of put these together. So this is acute. Obviously, this is less than 90 degrees. If theta equals 90 degrees, then you can say your vectors are orthogonal. And so if this is U, then V would have to look like that. They would have to form a 90-degree angle. So that's another option. And then the last option is if theta is equal to 0 degrees, then they are in the same direction. So if this is U, then V is in the same direction. So those are kind of some options when you get your theta value to know what your vectors are in relation to each other. Are they orthogonal? Are they in the same direction?